Great. And I'm really happy to introduce our next speaker, Austin Buchanan. Austin, could you, while I'm introducing you, start your screen share, please?
Sure.
So Austin is currently an assistant professor of industrial engineering and management at Oklahoma State University. His research focuses on solving combinatorial optimization problems in networks, funded by the NSF, including Career Award. And he currently serves as an associate editor for the journals Networks and Optimization Letters, a member of the council also for the Informed section on telecommunications and network analytics. And he's published in journals including OR, Informed Journal on Computing, Math Programming, MPC, Networks, and others. So without further ado, I'm very happy to have Austin talk about his work on political districting. Take it away.
Thank you. Thanks for the introduction, and thanks for the invitation. Maybe apologies in advance. The mowers just showed up at my house, so hopefully they'll stay away from my window for the time being. But I don't know how much I can do to stop the noises. But anyway, so this is joint work with my recently defended PhD student Hamid. So he just defended last week, and he'll be joining Rice next week as a postdoc. And then the work is also co-authored with Eugene, who graduated from Texas A&M last year. Okay, so any talk about districting needs to talk about gerrymandering and motivation for considering redistricting from the OR or optimization perspective. So I guess gerrymandering has a long history in the US, going back at least a couple centuries. And over the last 50 or 60 years has been the subject of a lot of Supreme Court cases. So a notable case is Westbury V Sanders back in the 60s, where different congressional districts had a very different population. So you'll see that this 5th congressional district had a population about 3 times that of another one of the districts. And in this case, this map was overturned as being unconstitutional, basically because the populations were so unequal, and the voters who were in that 5th congressional district, their votes were really just being diluted there. Over the last few years, there have been several notable cases regarding partisan gerrymandering. You'll see here a map from Maryland and another map from North Carolina. And the Supreme Court recognized that these were brazen gerrymanders, but said basically that this was out of the scope of the federal courts. And so this has led to maybe more work at the state level. So states get to set their own laws regarding redistricting, and also Congress has the ability to enact laws about redistricting. And now anytime you're trying to impose new laws, you may like to know what would be the effect of these laws. So if you're trying to control gerrymandering, you might want to keep a lot of counties intact, perhaps. So you leave, you don't give as much control to the redistricting process. And so Iowa is an example of a state where they're required to keep counties intact in their congressional districts. West Virginia also kept their counties intact after the 2010 census. And even in the case of North Carolina, their state constitution requires that they keep all counties intact. It turns out that some of their counties have too many people to be put into a single district, and so they must be split in order to not violate that kind of population balance constraint. And the state Supreme Court in North Carolina has responded to this by saying, well, maybe the way to interpret this law is that you should split a minimum number of counties. There are other optimization problems that you could come up with that may be insightful. Perhaps you'd like to know how many communities could be kept intact. And this is of importance for the Citizens Redistricting Commission in California, where one of the criteria they're tasked with satisfying is to try to keep as many communities of interest intact as possible. So maybe I won't talk about all of these other ones other than to say these rules that you might place on the redistricting process, you'd like to know if they'll restrain would-be gerrymanderers, but at the same time, you'd like to know if they would have any unintended consequences. So for example, it's been suggested that if you place a high priority on having compact districts, this may have the unintended or perhaps intended consequence of packing a lot of urban voters into the same district and diluting their voting strength. So this is something to be aware of, and something that if you're using optimization, you don't want to just say, we'll take the most compact districts as possible. That's not really the way you should look at it, but I think optimization can still be useful to tell you perhaps what would happen. And in any case, if you're trying to solve any one of these maybe stylized problems where you have a single objective or a single kind of hard constraint that you're trying to satisfy, it's always going to be important to impose contiguity. So 22 states require that their congressional districts be contiguous by law, and basically every other state enacts contiguous districts anyway. Okay, so maybe I'll talk about kind of a classical optimization model in redistricting, and it's something that we'll build off of when we start talking about contiguity constraints. So there's a paper of Hess and others published back in the 60s in OR, and in there they were trying to get a districting plan that was as compact as possible. And the compactness measure that they used was what they called the moment of inertia. And so it's maybe illustrated by this picture over here. So this represents 3 districts, and these blue squares each represent the center of a district. And all of the other nodes or counties or census tracts, whatever you're working with, should be assigned to those centers. And you're trying to select the centers and make these assignments so as to minimize this basically this cost of assignment, which in their case was related to the distances between these red nodes and these blue nodes, and also the populations of these red nodes. So the model that they proposed is more or less a constrained k-median model. Let me first talk a little bit about the notation, the input parameters. So they had k as the number of districts. We have population lower and upper bounds for each district, L and U. We also know the population in each county, or if you're working at the tract level or the block level, this could be for those different units. In our case, we'll be working with nodes in a graph. So each one of these nodes will represent a piece of land. And if 2 pieces of land, let's say counties, are adjacent, we'll connect them by an edge. And in their objective function, they also refer to the distances between these counties, which we measure as kind of the distances between the centers of these counties. And in this k-median model, we have the usual sort of variables. Xij, which equals 1 if vertex I is assigned to the district centered at vertex j. And so the particular case where I equals j, this xjj variable, this will tell you yes or no is a node a center of a district. Okay, so here's the model that they proposed. So here, this objective is to minimize that moment of inertia. It turns out that this coefficient, pi dij squared, it's just a constant. It doesn't really matter what this is. And in the rest of the talk, I'm just going to use this wij to represent whatever this penalty is. And then we have the usual sorts of constraints saying that each node needs to be assigned to one other center. So it'll be placed in one district. We should select k centers, which will then give us k districts. Anytime that a node is selected as a center, the total number of people assigned to that node is somewhere between L and U. And then we have usual kind of strengthening constraints and binary restrictions. But you'll see here that there's no explicit constraint that imposes contiguity, besides the inclination of the model to generate contiguous districts, just because it's compactness-seeking up here. Associated with this IP is an LP relaxation, and the feasible region of that will denote by P sub Hess. Okay, so if you solve that model for, let's say, the state of Oklahoma at the county level, and you require a 1% population deviation, this is the solution that you'll get. And so you'll see that the compactness-seeking objective is not enough to impose contiguity. So then the question becomes, well, how would you explicitly impose contiguity in the context of that model? And for many years, researchers have claimed that contiguity, these constraints really make districting a lot harder than other combinatorial optimization problems, even other partitioning style problems. And maybe the message from my talk today is that maybe contiguity is really not so bad. Maybe it's not the bottleneck. And as evidence of this, in the later slides, I'll show that we solve this Hess model with or without contiguity constraints for all county level instances in the US and half of the tract level instances. So these are at the census tract level. An example is for Indiana, which has about 1,500 census tracts. We're able to solve this instance under that particular stylized version of the problem that Hess considers under that moment of inertia objective. And then I think there are three keys to why we were able to do this. First, we've got maybe the right IP models for imposing contiguity. We also use a very simple heuristic, which is then employed in this last step, Lagrangian reduced cost fixing. And I'll talk more about that later, but the main idea is that most of these Xij variables will take a value of 0 in an optimal solution. And if you can predict upfront which ones of these variables will be 0, you can go ahead and fix them to 0 and not even include them when you're solving that root LP relaxation. Okay, so now I'll talk about 4 different models for imposing contiguity. So we have here, let's suppose we're considering this 5x5 grid instance. And for simplicity purposes, I'm going to suppose that each node has 1 person in it, and that we're trying to split up this instance into 5 districts, each with 5 nodes in them. So an example solution could be over here. And you'll see that I've colored 1 node inside of each district, which could be thought of as the center of that district. And if these districts are indeed contiguous, we should be able to send flows of that type. So you see here I have a red center and then I have red flows coming out of it. You should be able to send flows across only those nodes that have been assigned to this center. And that leads to this variable definition Fijv that tells you how much flow is sent across edge ij, and this flow is originating from V. So this leads to this existing model. And I think it's about what you would expect. There's this one constraint I want to mention, this constraint 2c, which tells you basically that you can only receive flow of a particular color if you yourself are assigned to that center. So you can only receive red flow if you yourself are assigned to the red node. And it has this big M sort of coefficient here. And so one of the first things we thought of when we saw this model is maybe you can reformulate this and avoid this big M constraint. So that'll motivate what I'll talk about on the next slide, but this model has an associated LP relaxation, and this P sub sure will be its feasible region. So the trick to strengthen that existing flow-based model is to define variables. Instead of for just a commodity for each node, we have a commodity for each pair of nodes. So not just for the center B, but for the pair of nodes A and B. So if you're trying to send flow from B to A across ij, this variable will take a value of 1. And this leads to I think a quite intuitive set of constraints. And you'll see here that we don't have that big M anymore. We just have a 1. This Strengthening comes at a cost. So you definitely have to pay for more variables, more constraints, more non-zeros. And maybe it's a computational question whether this is worth it. It turns out it's not, but it ends up being helpful in our analysis. Okay, I'd like to talk about two different cut-based models. So this one is an existing model, and it's based off of the notion of graph cuts, or maybe more specifically, A-B separators. So you can see in this picture that these red nodes, if you remove them from the graph, you will separate nodes 6 and 10. So this forms what you might call an A-B separator for this graph. And the way you would use this in the formulation is you would say, if you want to assign node 6 to node 10, and you want this district to be contiguous, you're going to also have to assign one of these red nodes to that same district. And so that leads naturally to this constraint saying, if 6 is assigned to 10, then at least one of these red nodes from this set C should also be assigned to this node 10. Okay. And I'll denote by P sub cut, it's LP feasible region. So, but what we noticed was that you can actually strengthen these constraints in the districting context. So we know that, for example, that the population of each district should be no more than U. And so we can exploit that in our constraints. So if we're looking at this same instance where we wanted to put 5 nodes in every district, and suppose that you're assigning node 6 to node 10, the only way you can do that is to take this path from 6 to 10, and so you would have to pick up node 8 along the way. If you don't assign node 8 to 10, then if you wanted to make 6 and 10 connected, you would have to have a total of 7 nodes, which would exceed our population upper bound. So you can write the same sort of constraint saying, if you assign 6 to 10, you would better also assign 8 to 10. Okay, so this leads to this PL cut, LP relaxation. And as you might expect, we have this set of inclusions comparing the strength of the formulations. So this length bounded cut model, or this L cut model, is the strongest. And this cut model ends up being equal in strength to that multi-commodity flow formulation. And that's just a straightforward max flow min cut type proof. And then last, we have that the multi-commodity flow formulation is stronger than this Shirabe formulation, and that's, you could see that as because this formulation is kind of an aggregation of this formulation. Okay, but these two cut-based formulations have exponentially many constraints generally, and so we have to ask the question about their separation problem. Is this an easy problem? And it turns out for this cut-based model, it is an easy problem to solve, which kind of, if you took the straightforward approach for the separation problem, you're going to solve basically a min-cut problem for every pair of nodes in the graph. So you solve basically n-squared min-cut problems. And it turns out, because these graphs are planar, you could exploit the planarity and solve min-cut in maybe n-squared or maybe even order n time. But that would still only give you maybe n to the 4th or n cubed. So it turns out there's a trick going on here, some very special planarity exploiting min-cut algorithms that allows us to solve this separation problem in almost linear time with respect to the number of entries in this X star solution. So X star has dimension n by n. However, for this L-cut model, it's generally an NP-hard problem for separation, but if this solution X star is integer, we can solve this in linear time in the size of X star. And in fact, in our implementation, we'll be using these linear time implementations. Okay, so before I give some experimental results, I'll just say we're using Gurobi. We have a 1-hour time limit. We pulled data from the 2010 census. The 2020 census numbers are not ready yet. And first I'll give some results at the county level. And for 27 of these states, there's just no way to redistrict at the county level. So for example, in the case of California, there's Los Angeles County, which has many millions of people. And you can't put this LA County into one district. It would just have too many people. So you want to have about 700,000 people per congressional district. So states like this, we say that they're overtly infeasible, and there's no reason to try to solve these instances. They're definitely infeasible. There are also 7 other states where the population of that state is so small that they only get 1 congressional representative, and so these instances are really trivial. So this leaves 16 instances that I'll give results for. Here I have some pictures, so you can see that for Oklahoma and for West Virginia, if you don't impose contiguity, or if you do impose contiguity, it does make a difference. So you really do need these constraints. Okay, and then I have some times here. So for the 4 different contiguity formulations, you can see that generally speaking, this L-cut model is the fastest, generally taking just a second or 2. There's one notable case of South Carolina where all 4 of these models run into a time limit of 1 hour. It turns out this instance is infeasible, and it's just a little hard to show that. So it turns out that every single node in this instance can be placed into a suitable district, but that you can't piece these districts together into a full districting plan. There's a small trick you can make, small adjustment you can make to this L-cut model. Basically, it amounts to some variable fixing, and it ends up being safe. And if you do it in this particular way, you can actually prove infeasibility of this instance in a few seconds. So we do know that this instance is infeasible, but not in the direct way that I've explained the model. Okay. So, but we'd maybe also like to see some tract level instances. And if you just send this Hess model or this Schur model to Gurobi, you're going to have problems. So these models grow, I guess the number of X variables grows like n squared. And so you can see very quickly that the number of variables is large, and actually we're not able to solve the LP relaxation within an hour. But when we can solve the LP relaxation, we can typically solve the IP. So it seems like the bottleneck is really solving that root LP. So how might we handle this? And as I mentioned before, most of these variables will take a value of 0. And we'd like to know which ones they are. So for example, if you're looking at a census tract over in the panhandle of Oklahoma, it's unlikely that that would be the center of an optimally compact district. And so we're able to argue that all of these green tracts cannot be optimal district centers under this compactness objective. And so all of these green tracts, we can fix their XJJ variables to 0. Meanwhile, you can maybe imagine if you're considering to assign this tract to maybe some tract way over here, that you would never want to do that. That would also not be optimally compact. And so in total, 99% of the XIJ variables were able to fix to 0 for Oklahoma at the tract level. And I think I don't have enough time to talk too much about the Lagrangian procedures that we're using, but it's I guess in this Hess case, it's basically the normal Lagrangian that you would see for the K-median problem. We just also have these population lower and upper bound constraints here. And if you solve this Lagrangian with a variable tentatively fixed to 1, and you find out that this objective is really bad, maybe worse than a heuristic solution that we found, then you know that this variable actually needs to take the opposite value. It must be 1, or it must be 0 in an optimal solution. And it turns out we can compute this Lagrangian objective value for all of these ST variables in a total of n squared time. So it's very, very quick. And we can also exploit contiguity, but I think I definitely don't have time to talk about this. I'll refer you to the paper for the details on this one, but it allows us to fix even more variables to 0 when we exploit that contiguity information. And in some cases, the number of fixings goes from something like 17% of the variables to 0 to 40% of the variables to 0. So this really is helping us. Okay, so you can see here the Lagrangian is pretty quick. Our heuristic is pretty quick, just a few seconds. And in the end, we're able to fix 90 to 100% of the variables to 0. Those are optimal solutions at the tract level. And let's see. Okay, so you'll see here I have 1 hour time limit for those 5 states. And you'll see that when we don't impose contiguity, and when we do impose contiguity with this cut-based model, the times aren't too far apart from each other. But there is more time spent if you're using this flow-based model. And in total, if you look at all of the instances that are solved in a 1 hour time limit, you can solve 16 without contiguity and 16 with contiguity. And they're the same 16 states. And in fact, whenever you're looking at those instances where you couldn't solve the MIP, but you could solve the LP within an hour, we can solve more of the cut model within an hour as opposed to the Hess model. And this is because we're exploiting contiguity and able to fix more of these variables to 0 up front. And there are 5 more instances that weren't in that 16 count. So these 5 instances we're able to solve, but it took more than an hour. So in total, I think it was 21 instances that were solved out of a total of 43. So if you exclude the 7 instances that are trivial because they just have 1 district. And I guess maybe I'll do a quick conclusion if I've got time. So yeah, we have an analytical and computational comparison of these models. I think on the county level instances, this SURE model works fine. But as you move to the tract level, it really is important to use these cut-based models. And I think for at least this objective function, the contiguity constraint, that's not really what makes these instances challenging. I think it's solving the root LP relaxation that's the biggest bottleneck. And maybe again, to reiterate, I don't think that the maps that we're generating are good. I don't even think they're legal. They don't consider things like the Voting Rights Act or racial representational goals or partisan fairness or anything like that. So again, I think the story here is about contiguity constraints, and that the techniques developed in this work could possibly be used to answer these more complicated socially aware districting problems. And I have QR codes for a preprint of the paper and also for our GitHub repo. So all of our code, all of our input data, everything is there. All of the maps, pictures, and also the block level solutions. We're representing the solutions at the block level. We tell you for each census block which district is it assigned to.
Well, thank you very much, Austin. So let's thank Austin virtually, and also Ricardo. And I think right now we are mostly running out of time, but if anybody has a quick question for Austin, I do, but I'll save it for the breakout room. If anybody has a quick question for Austin, you can ask it in the chat or raise your hand in the participants panel, and then I can unmute you. Well, if not, I will save my question actually for the breakout room. But yeah, let's thank Austin and Ricardo again. And I look forward to seeing everyone next week in another session of Dots. And again, I encourage everyone to. In the meantime, if you have any questions, I already actually posted one on the Discord channel, so you can ask questions of both speakers on the Discord channel, and I'll make sure to point it to them if there are any questions there. So Ricardo has one there already. Oh yeah, Austin too. Okay, great. And then also right now, what we're going to do is we're going to switch to the usual breakout rooms. And that's going to be one breakout room for Austin, one breakout room for Ricardo. Ricardo will be in breakout room 1. Austin will be in breakout room 2. And there's also going to be this general non-breakout room session where you can stay or leave the breakout room and join. And it's just going to be a general social gathering. You can have your tea, coffee, or beer if you're in Europe, maybe. So please stick around for that if you would like to.